Hello students, welcome to the class. So in the previous class, we have discussed about the Lewis structures for writing for different molecules. It may be for different ions or it may be for different polyatomic ions, which are cations, and polyatomic ions, which are anions. And we have seen different structures. Yeah. So I had said we will discuss about the characteristics of the covalent compounds. Now, how we have seen the characteristics, the factors favoring ionic bond formation. Similarly, we have factors favoring covalent bond formation. Ionic bond factors favoring ionic bond formation is one of the atoms should have low ionization energy and another atom should have high electron gain enthalpy, and lattice energy should be very negative. So these were the factors what we had seen. Apart from that, under covalent compounds, what are the conditions for a compound to form, for a molecules to form covalent compound? Yeah, the condition is that there must be very less electronegativity difference between the two atoms. The two combining atoms, they should have very less electronegativity difference, or the electronegativity difference should be zero only. When it will be zero, when it is between same atoms, or when it is less, when the electronegativity difference is very less, means what? It is between two non-metals only. Yes, so the combining atoms should be short of, second thing is, they should be short of 1, 2, or 3 electrons to complete the octet. If they are short of 1, 2, or 3 electrons, both the combining atoms, then surely it is going to be a covalent compound. Electronegativity difference should be very less, or it should be zero only. The approach of the atoms towards one another should be accompanied by how? The approach, when the two atoms are coming closer, there should be decrease of energy. The energy should reduce. There should be decrease of energy. So these are the factors which favor formation of covalent compound. Apart from that, what are the characteristics of covalent compounds? Covalent compounds, they exist as gases or they exist as liquid, whereas ionic compounds exist as solids, right? So under normal temperature and pressure, covalent compounds exist as gases and liquids. Yes. Then diamond, example, diamond you take, or carborundum, silicon carbide is called carborundum. Silica you take SiO2. Yes. Then aluminium nitride you take AlN. These have giant three-dimensional network structures. Therefore, exceptionally, they have high melting and boiling points. Otherwise, covalent compounds have relatively low melting and boiling points. Low melting and boiling points. Relatively, they have got low melting and boiling points. Third point, in general, covalent compounds, they are bad conductors of electricity. They are bad conductors of electricity. But under covalent compounds, if the covalent compounds are between same atoms, they are homoatomic. We say them as non-polar. But if the covalent compounds are between two different atoms, we'll discuss that. They are nothing but polar covalent compounds. Yes, if you have polar covalent compounds, say HCl, there is slight difference in the electronegativity, right? They conduct electricity, little electricity in solution. Yes, even graphite, even in solid state can conduct electricity. Why? Because electrons can pass from one layer to another. Graphite is present in the form of hexagonal layers, and there is free electron which can pass from one layer to another. Therefore, it conducts electricity. Okay. These compounds are generally insoluble in water because covalent compounds are non-polar compounds. Therefore, they will dissolve in non-polar solvents like alcohol. Yes, they will dissolve. Yes, and they will dissolve some covalent compounds like alcohol. Alcohol is a covalent compound. It dissolves in water. Now the question arises, alcohol being a covalent compound, it should be non-polar. Then why it dissolves in water? It is because alcohol has the tendency to form hydrogen bond with water. In the end of this topic, we'll discuss what are hydrogen bonds and all. That time I'll let you all know. So alcohol dissolves in water because of formation of hydrogen bonding. Yes, these covalent bonds are rigid and they are directional. They are very directional. Yes, covalent substances, they show molecular reactions. Ionic substances show ionic reactions. Covalent substances show molecular reactions. Ionic reactions are fast. Molecular reactions are slow. Yes. Next, the number of electrons contributed by an atom for sharing while with other atoms is called what? It is called covalency. Hence the name covalent compound. Like how you have electrovalency. Electrovalency is what? Number of electrons lost or number of electrons gained. What is covalency? The number of electrons contributed for sharing with other atom is called covalency. Yes. So covalency is equal to, how do we find covalency? It is equal to 8 minus the number of group to which it belongs. So group number to which the element belongs. Sometimes there is variable covalency also. And when you want to find variable covalence, that means many different covalencies we can find. It can share, in some cases it can share 1 electron, in some cases it can share 2 electrons, like that. That is called variable covalency. It is equal to total number of unpaired electrons in s, p and d orbitals of its valence shell. Yes, if you want to find covalency, variable covalency, it is equal to number of s, p, d electrons in valence shell. That is equal to variable covalence. Yes. So these are some of the properties of covalent compounds. Yes. So these are the covalent compounds, and this is Lewis representation. We call it as Lewis structures. Okay. Moving to the next one, formal charge. In polyatomic ions, the net charge is charge on the ion as a whole, and not by particular atom. Just now we had written, right? We had written this CO3 minus 2. So this is the charge. And this charge is not for oxygen or for carbon. It is for whole ion, whole molecule. So only I had written, when I was writing the structure, I wrote a box bracket like this, and then I wrote minus 2, right? Similarly, when you have NH4 plus, this plus charge is not for individual atom. It is for entire molecule. And that is for the entire whole atom, molecule and so. But if you want to find the individual charge carried, individual atoms, individual ions, what charge they carry, that is nothing but formal charge. So in polyatomic ions, the net charge is charge on the entire ion as a whole and not by particular atom. However, charges can be assigned to individual atoms or ions. And that is called what? That is called formal charge. Now, how to calculate formal charge? There is a formula. Formal charge denoted as Fc on an atom in a Lewis structure. Total number of valence electrons in the free atom. For a free atom, total number of valence electrons minus total number of non-bonding electrons. Okay, it is lone pair. It means lone pair, but you have to consider electrons. Minus half the total number of bonding electrons. So let me make this like this. So formal charge on an atom is equal to, formal charge on an atom is equal to what it is? Total number of valence electrons. So I will write valence electrons like this, minus total number of non-bonded electrons. Yes. So I will write L. Non-bonded electrons means lone pair of electrons, minus half into total number of shared electrons, S. So this is the formula for formal charge. V minus L minus half into S. So let us use that formula and find. Okay, O3 structure is be given. So O3 structure according to Lewis representation, this is the O3 structure. Yes, okay. So central oxygen is numbered 1, this is number 2, this is number 3. For any molecule if you take, you have to number them. Okay, so formal charge on first one, numbered 1, yes or no? Okay. So what is the valence electrons on all are oxygen? So valence electrons are 6 minus. How many electrons? Lone pairs, no. Lone pairs of electrons. How many electrons are there? Non-bonded electrons, 2. Minus half into. How many shared pairs this oxygen is involved? 1, 2, 3, 4, 5, 6. 3 bonds means 6 electrons. So half into 6 is 3. So 6 minus 2 is 4. 4 minus 3 is 1. So what is the charge carried by this oxygen? Plus 1. Okay, next. End oxygen atom marked 2. So second oxygen atom. 6 is the valence electron minus. How many non-bonded? 1, 2, 3, 4. 4 minus half into 1, 2, 3, 4. 4. So 2. 6 minus 4 is 2. 2 minus 2 is 0. So this is carrying 0 charge. Okay. third oxygen atom. 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 minus half into how many bonded electrons? 2. So 2 ones are 2 ones are 6 minus 6 is 0 and this is minus 1. So this is carrying minus 1 charge. Find out the total charge. O3, when you write O3, the total charge is 0 here. There is nothing mentioned, so it is 0. Correct? Let us verify. So first oxygen atom plus 1 plus second oxygen atom 0 plus third oxygen atom is minus 1 and the whole charge is what? It is 0. Let us verify, is it correct or no? Plus 1 minus 1 gets cancelled. What is the charge? 0 equal to 0. So our formal charge what we have calculated is correct. So formal charge gives us what? It gives us the charge carried by the individual atoms. It gives us the charge carried by the individual atoms. I can show you an example also. Suppose I have CO3 minus 2. Now see here, if they give you Lewis structure, it is well and good. If they don't give you Lewis structure, then what to do? Then we know how to find out Lewis structure. T is equal to V is equal to S is equal to U is equal to. T stands for total electrons, 8 carbon plus 8 into 3. 8 3s are 24, 8 4s are 32. So total electrons are 32. Correct? Okay. Valence electrons on carbon are 4 plus oxygen are 6. 6 into 3. Then minus 2 means what? Plus 2. 18 plus 2 is 20. 20 plus 4 is 24 electrons are valence electrons. Yes, T minus V. 32 minus 24 is how much? It is 8 electrons. And then 24 minus 8 is how much? It is 16 electrons. So we will write carbon in the center, oxygens, 3 oxygen atoms. Yes, and here this is the total charge, minus 2. Okay. How many shared? 8 electrons. 1, 2, 3, 4, 5, 6. And I can write double bond anywhere. Suppose I'll write it here. 7, 8. So are they 8? So 2, 4, 6, and 8. So these are shared. Unshared, you have to write such that every atom gets octet configuration. So here there are only 2. So how many remain? 1, 2, 3, 4, 5, 6. So this oxygen completes 8. Carbon 1, 2, 3, 4, 5, 6, 7, 8. It has already completed it. So there are no lone electrons. Here 4, 5, 6, 7, 8. Yes, here there is only 1. So 1, 2, 3, 4, 5, 6. Is that right? Or verify. 16. 2, 4, 6. 8, 10, 12, 14, 16. So this is the structure, Lewis structure for CO3 minus 2. Now I want to calculate the formal charge. There are 4 atoms. Okay, this I'll consider it as 1. This is 2. This is 3. And this is 4. Okay. Formal charge on oxygen number 1. Correct? Equal to. So we know the formula. What is the formula? The formula says V minus, so formal charge is equal to V minus L minus half into S. Correct? So what is V? Valence electrons on oxygen are 6 minus first oxygen. How many lone pairs? 1, 2, 3, 4, 5, 6 minus half into how many shared? 2 into 2. So this 1, this becomes 6 minus 6 is 0. So this becomes what? Minus 1. Okay. So the formal charge on this oxygen is how much? It is minus 1. Minus 1. Fine. Second one, formal charge on carbon, which is number 2. Carbon valence electrons are 4 minus how many lone pairs? 0 minus half into how many bond pairs? 1, 2, 3, 4, 5, 6, 7, 8. So 2 ones are 2, 4s are 8. 4 minus 4 is 0. So what is the charge on carbon? It is 0. It is 0. Okay. Formal charge on oxygen, which is number 3. So 6 is the valence electrons minus how many unbonded? It is 6. Non-bonded are 6 minus half into 2. Correct? So it is again minus 1. So here we have minus 1 on this oxygen again. Last one. Formal charge on oxygen number 4 is equal to 6 minus how many non-bonded electrons? There are 4 minus half into, again 4 are involved in bonding. So 2 ones are 2 twos are 6 minus 4 is 2. 2 minus 2 is 0. Yes. So this oxygen is having 0 formal charge. Now let us verify whether our answer is correct or no. So minus 1 plus 0 plus minus 1 plus 0 is equal to, what is the total charge carried? -2. -1 is what? -2. That is equal to -2. So this is how we calculate the formal charge and verify our formal charge. Is that understood? Clear? So this is how we calculate the formal charge. Formal charge is calculated. One more example I'll give you. Yeah. Okay. Let me say I have a molecule NO2 minus. Okay. So this is my ion, polyatomic ion. Now what I'll do, I'll first calculate T, V, S and U. Correct? I'll calculate all of them first. Okay. Total number of electrons on nitrogen are 8 plus oxygen are 8 into 2. 8 to the 16. 8 on 16 is a 24. So total will be what? 24. 8 3s are 24. Valence electrons on nitrogen are 5 plus oxygen are 6 into 2. Minus 1 means what? Plus 1. So 5 plus 1 is 6. 6 2s are 12 plus 2, 6 is 18. Correct? 18 electrons. Total T minus V, 24 minus 18 is how much? 6 electrons. Correct? Okay. 18 minus 6 is how much? It is 12 electrons. Is that right? Yes or no? Okay. So let us write the structure. Nitrogen at the center. More electronegative are oxygens. I will write 2 oxygen atoms at sides. Okay. How many electrons shared? 6. 1, 2, 3, 4. So one more, 5, 6. Wherever you want to put a double bond. So I will indicate them through a double bond. Okay. Now 12 electrons. Verify. Each atom should have octet. So here 4. How many more? 1, 2. So oxygen has completed its octet. Oh, okay. 2, 4, 6. So 6 are there. One more. So nitrogen will have 1 lone pair. Here there are 2. So 3, 4, 5, 6, 7, 8. Now let us, so I'll write this as minus. Is that right? Okay, verify 12 electrons, 2, 4, 6, 8, 10, 12. So this is my correct Lewis structure. Now what I will do, I will calculate the formal charge. What is the formula for formal charge? V minus L minus half into S. Okay, so let us calculate. Let me call this ion as 1, this as 2, and this as 3. So formal charge on oxygen numbered 1 is equal to, valence electrons are 6 minus how many lone pairs? 2 lone pairs means 4 electrons, minus half into bond pairs are 2 means it is 4. So 2 ones are 2 twos are. So 2 minus 2 is how much? 0. Okay, fine. Formal charge on oxygen number 2. 6 minus. So there are 6 lone pairs, lone electrons, non-bonded electrons, half into 2. 2 ones are 2 ones are 6 minus 6 is 0. This becomes minus 1. Formal charge on nitrogen, which is numbered 3. So nitrogen 5. There are valence electrons minus non-bonded electrons are 2 minus half into 2, 4, 6. 6 2 ones are 2 3s are 5 minus 2 is 3. 3 minus 3 is 0. Therefore, I can conclude saying oxygen, this oxygen it is 0. This oxygen it is minus 1 and this nitrogen it is 0. So calculate the total formal charge. 0 plus 0 plus minus 1 equal to, what is the total charge given? Minus 1. So minus 1 is equal to minus 1. Thus verified that the Lewis structure is also correct and formal charges on the individual atoms are also correct. So what does formal charge give us? Formal charge gives us the charge carried by the individual atom. Not only for ions, you can calculate formal charges for molecules also. That time here total will take it as 0. That's it. Okay. Now what is the significance of this formal charge? The significance of the formal charge is that it helps to select most stable structure. It helps us to select the most stable structure. That is one with which will be most stable. The one with least energy, that will be most stable structure. Yes, the most stable structure is the one which has smallest formal charges on the atoms. Which has got smallest formal charges on the atoms, that will be most stable structure. Because that structure will have least energy. So smallest formal charges is most stable because it will be having least energy. It will be having least energy. Understood? So this is how we calculate formal charges. I hope that is clear. So this is the formula. Is that fine? Yes? Okay. Now limitations of octet rule. So we have discussed what is octet rule, right? What is octet rule? All the atoms, they tend to have 8 electrons in the outermost shell. Why they tend to have 8 electrons? In order so that they will have the stable inert gas configuration. Yeah, to have inert gas configuration, they will try to have 8 electrons in the outermost shell. That will be stable configuration. So according to Lewis and Langmuir, that was the given understanding. Okay, fine. But there are certain limitations for this octet rule. Now, what are the limitations for the octet rule? Why, sir, in some cases, octet rule was not accepted? Why octet rule was not accepted? Okay, let us try to understand one by one. First point is incomplete octet. The first point is incomplete octet. Now, what does incomplete octet means? In some covalent compounds, the central atom, see, we know that according to octet rule, all the atoms should have 8 electrons in their outermost shell. All of them should have 8 electrons in their outermost shell, except for hydrogen and all. Hydrogen and all, there will be how many electrons? There will be, for hydrogen and all, if you see, there will be how many electrons? They will have 2 electrons, that is duplet, right? Okay, helium, it will be duplet, lithium will be duplet. Yes, so all the other atoms, either by transfer of electrons or by sharing of electrons, they will have 8 electrons in their outermost shell. They will have 8 electrons. But here we have something called incomplete octet. So now what does this incomplete octet means? In some covalent compounds, central atom has less than 8 electrons. So if you see lithium chloride, try to write the structure of lithium chloride. Lithium, it is 3, so 2 and 1. Chlorine, it is 17, 2, 8, 7. Okay, so by transfer of electron, this will have 2 electrons in its outermost shell. This will have 8 electrons. So this is the structure formed. So it is not having, lithium is not having 8 electrons in its outermost, in its shell when it is forming an ion. Even beryllium chloride, if you see, beryllium hydride they have given, BeH2. So beryllium, hydrogen, it will have duplet configuration only. But what about beryllium? Beryllium, after sharing one electron, hydrogen is having duplet configuration in both the cases. But beryllium should have octet configuration. Yes, but it is having how many electrons? It is having only 4 electrons. So it is incomplete octet. Boron chloride, BCl3, molecule exists. This molecule exists. So chlorine. So by sharing one electron, all the chlorine atoms are going to complete their octet. See, chlorine will complete its octet. All the chlorine atoms are completing the octet. But in case of boron, how many electrons are there? There are only 6 electrons. So this shows what? It shows incomplete octet. And such molecules are said to be electron deficient molecules. Molecules which are poor of electrons. So they are called electron deficient molecules. Yes. So they are called electron deficient molecules. So this is incomplete octet. Some of the atoms, they do not, some of the central atoms do not have 8 electrons in their outermost shell. And that is incomplete octet. Then odd electron molecules. There are certain molecules which have odd number of electrons in the octet. Odd number of electrons, the octet rule is not applied for all such atoms. They exist. For example, if you consider an ion or a molecule containing unpaired valence electron, we call it as free radical. It will have only 1 electron. Yes. So that species disobeys the octet rule. But explanation was not given. However, they are very unstable and they tend to combine. But still such ions as free radicals exist, right? But the octet rule is not verified there. Similarly, here you can see the examples. By sharing the electrons, nitrogen is having 1 electron here. So 2, 4, 6, 7. So this is odd electron molecule. Yes or no? This has completed octet. But here there is odd number. So such molecules, they exist, but octet rule could not explain how they are stable. How they are stable. Even here, 2, 4, 6 and 1 electron. So such molecules do exist, but stability was not explained based on octet rule. It was explained based on some other rule. Okay. Expanded octet. If you take some molecules like phosphorus pentafluoride, phosphorus hexafluoride, or sulfur hexafluoride. This is okay, S. So it is sulfur hexafluoride. Yes. If you take such molecules, they will have phosphorus, which comes below nitrogen. It is having 5 electrons. So all 5 electrons are involved in sharing with the 1 electron of each fluorine. 1 electron of each fluorine. So when fluorine atom shares 1 electron, it will complete, all the fluorine atoms will complete its octet. All the fluorine atoms will complete their octet. But what about phosphorus? See, phosphorus 2, 4, 6, 8, 10. Phosphorus is having how many electrons? It is having 2, 4, 6, 8, 10. Understanding, it is not having 8 electrons. It is having plus 2, that is 10 electrons more. Sulfur, if you see, sulfur, it is having 6 electrons in the valence shell. So 6 valence electrons are there. So each electron is going to form bond with each fluorine atom. Each fluorine atom. Okay. So here like this. By sharing electrons, all the fluorine atoms will complete their octet. All of them will complete their octet. What about sulfur? Sulfur will have how many electrons? It will have 12 electrons. 2, 4, 6, 8, 10 and 12. So it is 12 electron molecule. The central atom is having 12 electrons. Here the central atom is having 10 electrons. More than 8, right? So that is called expanded octet. So in many compounds, there are more than 8 valence electrons around the central atom. It is termed as what? It is termed as expanded octet. And here also octet rule was not explained. And these molecules do exist, students. They do exist. But on what basis? But not on octet rule. They exist based on different rule that we study later. We call it as hybridization. Understanding? So octet rule could not explain this. Incomplete octet was not explained. Expanded octet was not explained. So incomplete octet, electron deficient molecules show. Expanded octet, electron rich molecules show. What were the other drawbacks of octet rule? Some noble gases also combine with oxygen and fluorine to form number of compounds. See, noble gas, according to octet rule, what it says, noble gases have 8 electrons in their outermost shell. Therefore, they are very stable. They are very stable as they do not react with any other atoms. Their valency is entirely 0. But some noble gases like xenon, yes, some noble gases like xenon, it combines with oxygen and fluorine, reactive non-metals, to form a number of compounds. And some of the compounds are shown here. XeF2 it can form. It can form XeF2O it can form. Yes, you can see here. Yes. So here if you see, this is the molecule, xenon difluoride. This is the molecule XeOF2. This was not explained by octet rule, like how noble gas is forming a compound. Apart from that, the theory does not account for shape of the molecule. See, we have seen so many explanations regarding octet rule now. We tried to write the structure based on the octet rule. Yes or no? Lewis structures are all based on what? They are based on octet rule only, because every atom we try to give 8 electrons. But anywhere did we find the shapes of the molecules? No. Carbon dioxide we wrote straight. Water we wrote straight. When I was telling you about the Lewis structures, we said we have seen this, right? Water we wrote it like this. Carbon dioxide we wrote it like this. Yes, even NH3 I wrote it like this. We have seen this. Correct or no? So nowhere the shapes of the molecules were explained by the octet rule. Actually, those are not the shapes of the molecules. NH3 is having some different shape. Water is having some different shape. Carbon dioxide is having some shape. So it does not account for the shapes of the molecules. It does not give any idea about the energy of the molecules and the relative stability. It does not give you any idea regarding the energy of the molecules and the relative stability. Yes. So this is about the drawbacks of octet rule. Okay. Okay. There is one more bond which you call it as coordinate bond. A brief introduction for coordinate bond. This was skipped in your syllabus, but it is there for NEET. So this is a special type of bond, or you can say it is a special covalent bond. You know that covalent bond is formed by mutual sharing, right? Equal sharing. This is a special type of bond where shared pair of electrons, whatever electrons come, what we say a covalent bond, this is going to contribute 1 electron, this is going to contribute 1 electron. So this will have a shared pair of electrons, correct? So this shared pair of electrons is contributed by atom A as well as atom B. But in coordinate bond, what happens? One will be electron rich, another one will be electron poor. So this is having 2 electrons, this is not having any electron. So what A will do is, it will contribute both of its electron pairs, both of its electrons, such that these 2 electrons are shared by A as well as they are shared by B. Understanding? Unlike covalent. Therefore, I said it is a special covalent bond. So covalent bond you indicate by a bond. Then how do you indicate coordinate bond? I will indicate it like this. That means the electron pair is contributed by atom A and it is shared by both. Understanding? It is contributed by atom A and it is shared by both. Simple example I will give you. If you consider NH3 molecule, we have seen the structure. Nitrogen has got a lone pair, unbonded electron pair. And if you consider BF3 molecule, it comes under incomplete octet, electron deficient molecule. Boron, if you see, write the structure and see, it is having only 6 electrons. It should have 8, right? So what nitrogen does is, I'll show you complete structure. This is H, H, H. This is one pair plus boron F3. So what nitrogen does, it will contribute its electron pair to whom? To boron, such that this electron pair is shared by nitrogen as well as by boron. Therefore, I can write it as, NH3, I will write it like this. So NH3 and electron pair is contributed by nitrogen to whom? To boron, BF3. Understanding? So you see, nitrogen is also having 8 electrons. Now boron is also having 8 electrons. And such bond is called what? It is called coordinate bond. Yes. So the atom which is contributing electron pair is called donor atom. The one which is sharing the electron pair is called acceptor. So donor is called as Lewis base. It donates electrons, shares electrons. And this is called as Lewis acid, acceptor. Yes, and it is usually shown by an arrow mark. It is usually shown by arrow mark. Example, in a CO molecule, carbon monoxide, there is a coordinate bond. There is a coordinate bond. Okay, so this is about the coordinate bond. A small little introduction regarding the coordinate bond. Fine. Okay. Bond parameters. So what are bond parameters? Bond parameters, covalent bonds are characterized. Covalent bonds can be characterized on the basis of bond parameters such as bond length, bond angle, bond order, bond energy. Bond energy is also known as what? It is also known as bond enthalpy. In some cases, it is also known as dissociation energy. It is also known as dissociation energy. Okay, fine. So let us try to understand. These bond parameters offer an insight into the stability of the chemical compound and the strength of the chemical bonds holding its atoms together. First one, bond length. It is defined as the equilibrium distance between the centers of the nuclei of two bonded atoms. It is expressed in terms of angstrom. Angstrom, okay. Experimentally, it can be defined by X-ray diffraction or electron diffraction methods. Okay, you can see here. So bond length is what? It is a measure of distance between the nuclei. See, there are two bonded atoms, pink color and orange color. These are atoms. They are bonded together. And these are the nucleus of the two atoms. Okay, so the internuclear distance, or you can say distance between the nuclei of two chemically bonded atoms is called what? It is nothing but bond length. Yes, approximately if you speak about the bond length, what is bond length? It is equal to sum of covalent radii of two bonded atoms. Yes or no? So these are the two covalently bonded atoms. This is radius of first atom, radius of second atom. Sum of the radii is nothing but bond length. It is nothing but bond length. So for covalent bonds, the bond length is inversely proportional. The bond length is inversely proportional to bond order. I'll tell you what is this. When we discuss what is bond order first, then we'll go for it. Which are accompanied by stronger force of attraction holding the atoms together. See, as the bond order decreases, as the bond length, this is the length of one bond, let me say, this is the length of one more bond. So as bond length increases, see, as the bond length increases, the internuclear distance increases. Yes or no? Bond length is increasing means what? Internuclear distance is increasing. So I can say nuclear attraction will be less. Therefore, I can break the bond very easily. Yes. But if bond length is short, what will happen? The nuclear attraction is strong, holding the two atoms together. Correct? Therefore, if I want to break the bond, I will have to put more energy. Therefore, I can say as bond length increases, the energy to break the bond decreases. Or as bond length decreases, the energy to break the bond increases. Energy to break the bond increases. Yes. So an illustration describing the bond length of a covalent bond in terms of sum of individual radii. This is an example. Okay. Bonded atoms tend to absorb, whatever bonded atoms are there, they tend to absorb thermal energy from the surroundings and they constantly vibrate. This vibrations causes the bond length to vary. Therefore, it is important to note that bond length of a covalent bond represents average distance between the nuclei of the two combining atoms. Understood? So this is about the bond length. Is that clear? Okay. Next, bond angle. Okay. What do we mean by bond angle? Angle between the lines representing the orbitals containing bonding electrons. Or whenever I speak about some bond, say, if I consider H2O molecule, actually the structure of H2O molecule is this. Okay, fine. And hydrogen has completed the duplet, oxygen, there are electrons like this. Okay. Now see, this dash represents what? Represents bond, 2 electrons, and this represents bond. What type of electrons? They are shared electrons. They are what? Shared electrons. So how do we define bond angle? Bond angle is defined as the angle between two covalent bonds. The angle between two covalent bonds, or the angle between two shared electrons, two covalently shared electrons. And bond angle in water molecule is 104.5 degrees. 104.5 degrees. This is the bond angle between the two covalent bonds. Yes. So the geometric angle between any two adjacent covalent bonds is called bond angle. This bond parameter, it provides the insight into the geometry of the molecule. So if I say bond angle is 180, what does that mean? That means the two bonds exist like this, and so geometry will be what? It is linear. Understanding? So it provides us about the shape of the molecules. If I say bond angle is 120, that means there are bonds which are present like this. Correct? This is the center molecule. Angle is 120 everywhere. So everywhere angle is 120 means what? The geometry of the molecule is trigonal. Understanding? Bond angle is 90. It means what? The geometry is something like this. Here the bond angle is 104.5 degrees. 109.5. Yes, the bond angle is this. So the geometry is tetrahedral. Yes, so depending upon the bond angle provides us what? Bond angle provides us the insight into the molecular geometry. Geometry means what? Molecular shape of the compound. So it helps in determining the shape. It can be expressed in degrees. Bond angle can be experimentally determined by spectroscopic methods. So you can see here, linear, two pairs, 180 degrees. Trigonal planar, 3 pairs are there. Bond pairs these are. So here the 120 degree. So it is trigonal planar. Tetrahedral. 4 bond angles, bonds are there. 109.28 minutes. Trigonal bipyramidal. 5 are there. 1, 2, 3, 4, 5 bonds. One side there is 90 degrees. In some other bonds, there is 120 degrees. Octahedral, 6 bond pairs everywhere, 90 degrees. Understanding? Understanding. So what does bond angle provides us? It provides us an insight information regarding the shapes, that is the geometries of the molecules. When we speak in chemistry, we say it as the geometry of the molecule. Geometry of the molecule. Coming to the next one, that is bond energy, which is also called as bond enthalpy. Bond energy, bond enthalpy. So bond enthalpy, it is defined as amount of energy required to break 1 mole of bonds of a particular type to separate them into gaseous atoms. For example, let me say I have H2 molecule. Yes, H2 molecule has HH bond. So if I want to break 1 mole of this HH bonds, what energy I need to break the bonds? That is called bond energy, or we call it as bond enthalpy. Yes, so bond energy is what? It is a measure of what then? It is measure of strength of the bond. You are requiring more energy means what? To break a bond, you are requiring more energy means what? That means the bond is very strong. You are requiring less energy to break the bond means what? That means the bond is very weak. Therefore, what does the bond energy tell us? It tells us about the strength of the bond. So bond energy is the measure of strength of the bond, how strong the bond is. It can be defined as the energy required to break all the bonds of a specific type in 1 mole of a chemical compound, which is in gaseous state. Which is in gaseous state. So when I say it is in gaseous state, it means what? Suppose I have this. So let me say here there are H2 gaseous molecules present. Correct? These are present. These are the gaseous molecules present. Okay. So when I put certain energy to this, then these bonds break. Yes, they break. So they break into what? They break into constituent atoms. If they are molecules, they break into constituent atoms. If they are polar molecules, they break into constituent ions. So they will break like this. So they will break like this. So here the bonds have been broken. Correct? So they have been broken. So bond breaking has taken place. So bond has broken here. Can you see here? Yes. So when I put certain energy, the bonds, 1 mole of bonds, they break to form constituent particles. And that energy which is required to break the bond is called bond energy or bond enthalpy. Bond energy or bond enthalpy. It is very important to note that bond energy is not the same as bond dissociation energy. So what do you mean by bond dissociation energy? It is change in enthalpy which is associated with homolytic cleavage of a bond. When you want to break a bond symmetrically, suppose the molecule is between similar atoms. When I want to break this bond, symmetrical breaking, then what energy I put, I call it as bond dissociation energy. Yes. So bond dissociation energy is not as same as bond energy. Now, what are the factors which affect this bond energy? Okay, what are the factors? See, suppose I'll give you some examples. Say, I have HF molecule. I have HCl molecule. I have HBr molecule. I have HI molecule. Why I have written like this? Because as you move down the group, atomic size increases. Correct? Atomic size is increasing. So as atomic size increases, the distance between the two nuclei increases. So when I say distance between the two nuclei, can I say bond length? Correct? Okay. So as distance between the two nuclei increases, as bond length increases, where I can break the bond very easily? Can I break the bond in first case very easily or in the last case? In the last case. So can I say as bond length increases, bond energy decreases. As bond length increases, bond energy decreases. It reduces. So I can say that bond energy is inversely proportional to bond length. Bond energy is inversely proportional to bond length. That is, longer bonds they have lower bond energies. They have lower bond energies. Yes or no? They have lower bond energies because they are long. Electrostatic force of attraction are less. Therefore, they can be broken very easily. Therefore, bond energy decreases. Whereas shorter bonds have higher bond energies. Shorter bonds have higher bond energies. Second point, bond energy is directly proportional to bond order. Yes. Now, what do we mean by bond order? Bond order means the number of bonds between the two combining atoms. How many bonds are there between the two combining atoms? That is bond order. For example, hydrogen molecule. Between two hydrogen atoms, how many bonds are there? One. So bond order is one. For oxygen molecule, how many bonds are there between two oxygen atoms? There are two bonds. Therefore, bond order is two. For nitrogen molecule, how many bonds are there between two nitrogen atoms? There are three bonds. Therefore, bond order is three. For ammonia molecule, NH3, how many bonds are there between two atoms? See, you cannot say three. Between two atoms, there is a single bond. Two atoms, there is a single bond. Two atoms, there is a single bond. So, bond order is what? It is one. So, between the two combining atoms, how many bonds are there? That is bond order. So, what happens as bond order increases? Just imagine, okay. So, there is a single bond order is one here. Here the bond order is 2 and here the bond order is 3. As bond order increases, bond order means what? Number of electrons. So as this bond order increases, the atoms come closer. So I can say as bond order increases, the internuclear distance decreases, atoms come closer. That means what? Bond length will decrease. Bond length decreases. So as bond order increases, bond length decreases. And as bond length decreases, bond energy increases. Therefore, we say bond energy is directly proportional to bond order. As bond order increases, bond energy decreases. Why? Because as bond order increases, the length of the bond, as bond order increases, the length of the bond decreases. As bond length decreases, the energy required to break 1 mole of such bonds becomes more. So bond energy increases. Bond energy increases. Therefore, we say bond order is directly proportional to what? It is directly proportional to bond energy. Third point, it is inversely proportional to. The bond energy is inversely proportional to the atomic radii. It is inversely proportional to the atomic radii. As atomic radii increases, what happens? The bond length, the distance between the two bonds increases. So when distance increases, bond energy decreases. Yes. So the first factor is as bond length increases, the bond energy decreases. Second factor, as bond order increases, the bond energy increases. And third factor, as atomic radii increases, the bond energy decreases. So I say bond energy is inversely proportional to bond length. Bond energy is also inversely proportional to atomic radius. But bond energy is directly proportional to bond order. It is directly proportional to bond order. So I can say lesser the bond order, what will happen? Lesser the bond order, what we say, higher is the bond energy. Lesser the bond order, higher is the bond. So bond energy, amount of energy required to break 1 mole of bonds of particular type to separate them into gaseous atoms. Bond enthalpy is also known as bond dissociation energy in some cases, that is homolytic cleavage, or simply bond enthalpy. Unit of bond enthalpy is kilojoules per mole. Yes, that is energy. Therefore, unit is kilojoules per mole. Greater the bond enthalpy means what? Stronger is the bond. Therefore, bond enthalpy is the measure of strength of the bond. How strong is the bond? We can say by looking at the bond energy. For example, hydrogen bond enthalpy in hydrogen is 435.8 kilojoules per mole. What does this mean? It means that to break 1 mole of hydrogen bonds in hydrogen molecule, to break 1 mole of bonds in hydrogen molecule, I need to put how much energy? I need to put 435.8 kilojoules of energy. The magnitude of bond enthalpy is also related to bond multiplicity. What is bond multiplicity? It is nothing but bond order. Greater the bond multiplicity, more will be the bond enthalpy. For example, you can see carbon-carbon single bond is there, 347 kilojoules is required. While carbon-carbon double bond, 610. See, as bond order is increasing, bond energy is increasing. Why? As bond order increases, the two combining atoms come closer. When they come closer, bond length will decrease. When bond length decreases, the energy will increase. In polyatomic molecules, the term mean or average bond enthalpy is used. Mean or average bond enthalpy is used. Can you see here? Carbon hydrogen 413 kilojoules per mole. So it is measured in kilojoules per mole. Look here, carbon-carbon single bond 348. Okay, let me mark it out. Carbon-carbon single bond 348 kilojoules per mole. Carbon-carbon double bond 619. So carbon-carbon single bond is 348 kilojoules. Carbon-carbon double bond is 619 kilojoules. Carbon-carbon triple bond is 839 kilojoules. So what is happening? Bond order is increasing. Therefore, bond energy is also increasing. As bond order increases, bond energy also increases. You observe in this set also. Observe here. Observe here. What is happening? Atomic size. Hydrogen, I'm not speaking about hydrogen. Fluorine, chlorine, bromine, iodine. As you move down the group, atomic size increases. So when atomic size increases, naturally bond length also increases. So what is happening? As bond length increases, this is having longest bond length. So bond length is increasing down the group. Yes, as you move down, the bond length is increasing. What is happening to the bond energy? Bond energy is decreasing. See, HF 567 kilojoules per mole of energy, HCl 431 kilojoules per mole of energy, then HBr 366 kilojoules per mole of energy, HI 299 kilojoules. So as bond length increases, when bond length is increasing, when atomic size is increasing. So as atomic size increases, the distance between the nuclei, that is bond length, is increasing. As bond length increases, the bond energy is decreasing. Therefore, we say they are inversely proportional to each other. It also depends upon the electronegativities. It also depends upon the electronegativities. Now, if you observe in these cases, observe these cases here. Observe here. Now see, electronegativities are different here. Fluorine is most electronegative. Then comes oxygen. Then comes chlorine. Correct? So as electronegativity is more, they are held strongly. They are held. So here there are both which are equally electronegative. So repulsions are there. Therefore, the bond energy becomes 190. But if you see oxygen and chlorine, there is electronegativity difference, certain electronegativity difference. This makes it more giving more bond energy, 203 kilojoules per mole. So all these are the factors which affect the bond energy. These are the factors which affect the bond energy. Okay. Then what is bond order? Just now we have seen. According to Lewis, in a covalent bond, the bond order is given by number of bonds between. The bond order is given by number of bonds between the two atoms, the two combining atoms in a molecule. For example, bond order of H2, it is 1. O2, double bond, it is 2. Then N2, it is 3. So I can conclude saying single covalent bond, bond order is 1. Double covalent bond, bond order is 2. Triple covalent bond, bond order is 3. Now what if I say bond order is 0? What does this mean? Bond order is 0 means what? It means the two atoms in a question are not covalently bonded. They are not covalently bonded. So I say no bond exists. If bond order is 0, no bond exists. No bond exists. Isoelectronic molecules and ions have identical bond orders. They have identical bond orders. For example, F2 and O2 minus 2. Minus 2 means this you will understand. See, this you will better understand when we will discuss some theory called molecular orbital theory. Yes, how do we get this? I will explain you there. Last part of this topic. That time also we can calculate bond order. There is some formula for calculating bond order. The formula for calculating bond order is number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. We use this formula and calculate. Yes. So what are bonding molecular orbitals, anti-bonding molecular orbitals? We'll all understand it in molecular orbital theory. That time we say isoelectronic molecules, if they are, then bond order is same. The bond order will be same. It will be same. Yes. So with the increase in bond order, bond enthalpy also increases, but bond length decreases. Bond length decreases. For example, N2 bond order is 3, bond enthalpy is 946 kilojoules per mole. For O2, bond order is 2, bond enthalpy is 498 kilojoules per mole. Yes, see here. So as bond order increases, the bond enthalpy also increases. Resonance structures we will take up in the next class. Hope you have followed with all the bond parameters and all. Do practice the relations between the bond parameters. Yes, resonance structures, I'll take it in the next class. Thank you.